Hi students, Miss Vernon back with day 2 of lesson 2.4. Today we're going to add on to what we did yesterday, talking about what's called the rational root theorem. And we'll be talking about how we can use synthetic division to break down polynomials into factored form so that we can then apply our concepts from 2.3. We'll also be learning about what's called an upper and lower bound test, which can help us narrow down which possible rational zeros or rational roots we should test. Let's go ahead and begin. There are 3 types of zeros that can exist in a function. We can have what's called a rational zero. A rational zero is a zero that can be graphed. It's found and used with synthetic division. These are the zeros you can see on the graph, and they'll come out of the rational root theorem. The second type of zero we can have is what's called an irrational zero. An irrational zero can also be graphed. However, you can't find them using synthetic division. An irrational zero is a zero that continues on forever without any pattern. So an irrational number would be like pi or the square root of 2. Those are irrational numbers. They're going to be found after doing synthetic division, and typically they will come out of using the quadratic formula. The third and final type of zero we can have is what's called a complex zero. A complex zero includes zeros that have an I or imaginary number in them, and they cannot be graphed as they're invisible, so they aren't viewed on a graph. They're calculated by using the quadratic formula, or they would be given to us in a problem, and we would break down a polynomial because we know about that complex zero. So let's just practice generally recognizing different types of zeros and working with them. So I have 2 problems here. In the first problem, I'm just going to draw in my line, and then we'll go ahead and balance. So I'd add 9 to both sides. So we'd get 4x squared equals 9. And then I'd divide by 4. X squared equals 9/4. And then next, we would take the square root of both sides, and we would get x equals, sorry, let me switch back to black, x equals plus or minus, the square root of 9 is 3, and the square root of 4 is 2. Now, 3/2 is what we call a rational zero. So a rational number is any number that can be written as an integer or as a fraction of integers. So this is a rational zero, and there are 2 of them. There is the positive 3/2, and then there is the negative 3/2. Okay, let's take a look at the next one. Again, I draw my line down the equal sign. I'm going to add 2 to both sides, giving me x squared equals 2. And then taking the square root of both sides, always remembering that when solving and taking the square root, you're going to have x equals plus or minus the square root of 2. Now, the square root of 2 is an irrational number, so this would be an irrational zero. And so we would not be able to calculate this using synthetic division, but it would be used later in the process through solving. Okay. All right, let's go ahead and take a look at how this connects to our rational zeros theorem. So our rational zeros theorem basically tells us how many possible or potential rational zeros exist. So our degree tells us how many exist, and our rational root theorem tells me which ones we might want to test. And so how the rational root theorem works is we are going to take and look at our polynomial function, and we can determine the potential roots by taking the last number, or our constant, divided by our leading coefficient, which would be q. And so what we do is we take those two numbers, and we would have p divided by q, and you would take all factors of P and divide them by all factors of Q. And then we also would have positive or negative in front of it because we don't know if they're, depending on the combination, it could be a positive or a negative. So for some polynomials, we end up having like 16, 18 different possible rational zeros you could have. But then others, we're only going to have 4. So it kind of depends on the situation. So let's take a look and apply this in a real problem. So to begin, we are going to identify all the possible rational zeros that exist using the rational root theorem. So as I look at this, I first check it's in standard form. So P is the last number and Q is the leading coefficient. So if I'm looking at P divided by Q, I would be looking at the factors of 2. So 1 and 2, 1 times 2 is 2. And the factors of Q are 1 and 3. Next, I have to come up with the list of possible rational zeros that I will want to check for. Now, it's any combination of these. And so I'm going to go ahead and try my best to help you see this. So I like to go 1 divided by 1, so plus or minus 1. And then I go to the next top number, so 2 divided by 1, so that would be plus or minus 2. Then I go back to the first number and I divide it by the second number on the bottom. So 1 divided by 3, so plus or minus 1/3. And then I have 2 over 3, which would be plus or minus 2/3. So in this case, I have 4 potential zeros that are available for us to work with. So what I'm going to do next is I'm going to figure out my synthetic division, and I'm going to figure out which ones should I do synthetic division with in order to break down this polynomial. So I'm going to graph this original polynomial, and it appears like I can see all 3 of my zeros. So that tends to lean me towards saying all of these zeros are going to be rational or irrational. But as I look at this, this appears to be -2. And that's one of my possible rational zeros. This also looks like it's a +1. Now, this one could be -1/3 or it could be -2/3. I don't know. So I'm going to need to do some synthetic division to break this down. So what I'm going to do is on my shelf, I'm going to place -2 because it's the first zero, farthest left zero. I'm then going to take each of the coefficients and place them on the top line so that I can set up to do my synthetic division. Now, when doing synthetic division to break down a polynomial, it is done slightly different, but you'll see a lot of the same process take place. So recall, synthetic division, we dropped our first number and then we multiplied. Next, we added these together and we got -2. -2 times -2 is a +4. -5 plus 4 is -1. -1 times -2 is +2. And -2 plus 2 is 0. So what this tells me is that I have a remainder of 0. And that means that that was indeed a 0 of our polynomial. So I can kind of think of this like a summary statement, a polynomial summary statement. So I would have x plus 2 is a factor because -2 is our 0. And this would leave me with my constant, my x, and my x squared. So I would have 3x squared minus 2x minus 1. Now, at this point in time, you have a choice. As soon as it becomes a quadratic, you could take that answer and factor it and find your remaining two factors. However, I'm going to go ahead and do synthetic division again because I really believe it passes through 1. So this time I'm going to do synthetic division with 1 on my shelf. But this time, instead of using my original polynomial, I'm going to use my quadratic that I was left with. So my top line will be 3, -2, and -1. This is going to allow me to factor this without ever factoring. Dropping my 3 and then multiplying, I get 3. -2 plus 3 is 1. 1 times 1 is 1. And -1 plus 1 is 0. Again, getting that remainder of 0 tells me that it does divide evenly. And that's great because now I know that I was able to find another factor. Notice I still have my x plus 2 factor, but now I know that x minus 1 is also a factor. And then I can take my last line. I have my constant, and this would be my x term. So I'd have 3x plus 1. I have just factored my initial polynomial completely, and I would be able to analyze it or understand it better. Awesome job. This is known as a linear factorization when we get it into all factors that have an x plus or an x minus, your different terms. All right, we have one last concept that I want to teach on today, and that is upper and lower bounds. So upper and lower bounds are a way to reduce the number of zeros that you might have to test. So if you're given a polynomial with a degree that is greater than 1 and a positive leading coefficient, we can do synthetic division to determine if there are zeros that will fall beyond or outside of a certain window. So how this works is there are two tests that take place. So if k is greater than 0, or if the shelf number is positive, so if the number on the shelf is positive, and the last line is non-negative, that means positive or 0, then we say that that value is an upper bound. And so basically what that means is it means that the graph will not have any x-intercepts that are larger than whatever you divided by your shelf number was. All right, so then the second test or portion of this is what we call a lower bound. So we can do a lower bound test if the shelf number is less than or equal to 0. It would be a lower bound test. And with a lower bound test, the last line needs to alternate negative and positive. So non-negative and non-positive, or negative, positive, negative, positive. If this happens, we say that k is a lower bound. And just like with the upper bound, what this means is it means that there would be no x-intercepts that would be smaller than that k value. All right, let's take a look at what this would look like in the context of a problem. So here we have a polynomial of degree 4. If I were to list out all the possible roots of this, I would have p divided by q. And so my possible roots would be quite extensive. I'm just going to go ahead and drag this down there for a second. And I would have factors of 8. So 1, 2, 4, 8. And I would have factors of 2, so 1 and 2. So factors of 8, or all the different combinations that exist, would be plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8, plus or minus 1/2. That's 1 divided by 2. 2 divided by 2 is 1, already covered. 4 divided by 2 is 2, covered. 8 divided by 2 is 4, covered. So I would have to do synthetic division with potentially 2, 4, 6, 8, 10 different values. That's a lot. So how a question might be worded is prove that all the real zeros lie on this interval. So when doing the upper and lower bound test, we don't care about the remainder of 0. We care about what's happening in that last line. So we'll start with the lower bound test first. And in the lower bound test, we are going to put -2 on the shelf because that's the number we want to test with. Next, I'm going to go ahead and place each of my coefficients on that top line. So I have 2, -7, -8, 14, and 8. Again, notice I do have 4th power, 3rd power, 2nd power, 1st power, 0 power. All right. Next, I'm going to drop the first number down and do my synthetic division. 2 times -2 is -4. Adding this up, I get -11. -11 times -2 is +22. Adding that up, I get 14. 14 times -2 is -28. 14 plus -28 is -14. And -14 times 2 is 28, which 28 and 8 is 36. Notice that this last line is alternating. So it alternates positive and negative. So therefore, I can state that -2 is a lower bound. Now you might say, well, Ms. Vernon, great, it's a lower bound. What does that mean? Well, what it means is I would not have to test -4 or -8 because I know that those are not going to be zeros because they're smaller than -2. So it's a way to eliminate having to test more values. All right, let's go ahead and apply the upper bound test. So the upper bound test must be done with the positive number. So in this case, that's a 5. And again, I use the same coefficient. So 2, -7, -8, 14, and +8. And remember, this time, we're hoping that that last line is all 0 or positive. So again, I drop down my 2 and I multiply. That gives me 10. -7 plus 10 is 3. 3 times 5 is 15. -8 plus 15 is 7. 7 times 5 is 35. 35 plus 14 is 49. And 49 times 5 is 245. Adding up, we get 253. Now, again, I don't care as much about the remainder. What I do care about is that these are all positive or 0. And because of that, I can state that 5 is an upper bound. So therefore, I know that I would not need to test +8 because, hey, it can't be greater than 5. So I've eliminated all of this. I've eliminated the -4 and technically the -2 because it wasn't a 0. So now I've reduced the number of zeros I need to test by 4. That saves a ton of time. Back in my time of doing math, we had to do this all by hand. We weren't able to use a calculator to narrow down which ones to check. All right, friends, that is your lesson for today on the rational root theorem, synthetic division to break down a polynomial, and upper and lower bound tests. Tune into class for more on this concept. Bye.